Welcome to Tomorrow Unveiled. If you've been following the robotics sector, you know that the last few years have felt like a slow, steady climb up a very slippery slope. We've seen incredible advancements in artificial intelligence on the digital side, and we've witnessed flashy, almost acrobatic demos of hardware. But often, well, that was followed by cautious skepticism about their real-world viability. But this past week, it genuinely felt like the entire industry didn't just climb a hill. We crested a major mountain range, fundamentally altering the landscape of what's possible in physical AI.
That's precisely the consensus gathered by the research team that compiled this information.
Yeah.
We are marking this moment as the crossing of a critical phase, what we are calling the embodiment threshold.
The embodiment threshold. Okay.
This is the point where the advanced generalist AI models, the ones that have been dominating the news and research in the virtual world, are now demonstrably and effectively integrated into sophisticated, durable physical hardware. It's the inflection point where theoretical intelligence gains practical, scalable bodies.
And what's taking central stage in this physical revolution is the humanoid form factor.
Right.
We see companies pouring absolutely massive resources into bipedal, two-armed designs, and every time some observers ask, why the uncanny valley? Why not just stick to highly specialized industrial arms bolted to the floor or, wheeled platforms? Our sources make the strategic consensus crystal clear. It's not about aesthetics, and it's certainly not about trying to trick us. It's about universal compatibility.
That's the key business decision driving this investment.
Ah.
Absolutely. Think about the environment these robots are entering. The human environment, from factories and industrial zones to retail stores and future homes, it's already designed for bipedal, bimanual operation. The standard width of a doorway, the height of a shelf, the design of a staircase, the tools on a workbench, they are all human-centric.
So by using the humanoid form, these new machines become essentially drop-in solutions.
Exactly. They can navigate the same spaces, open the same doors, use the same tools, and interact with infrastructure designed decades ago, all without requiring companies to spend millions or perhaps even billions on costly infrastructure modifications. Unlike specialized industrial robots that perform one narrow, highly optimized task, humanoids promise true, general-purpose versatility. That's the economic engine driving this design choice.
So today on Tomorrow Unveiled, we are distilling the key findings from our dedicated research team regarding the three interconnected pillars of this renaissance. First, the new AI brains that allow these machines to think, reason, and learn at scale. Second, the resilient hardware that makes them durable enough for continuous operation in the chaotic real world. And finally, the strategic corporate base for the real-world data that fuels the entire learning system.
Okay, so if the hardware is the body that crosses that embodiment threshold, the software that enables it is the central nervous system. What's truly fascinating in the research this week is the rapid and, aggressive standardization around a common technological thread. Vision Language Action, or VLA, models. This unified approach is quickly becoming the consensus central nervous system for all intelligent robots.
VLA, Vision Language Action. Okay. That sounds like we are, in effect, mashing together the large language models we've become familiar with, like advanced ChatGPT with a camera and a set of motors. But how does that convergence actually work, and how is it an improvement over older, more rigid robotic programming?
Well, it's the unification of capabilities executed in an incredibly sophisticated way. You see, VLA models unify the robot's perception, what it sees, with abstract goals, what you tell it to do via natural language and physical execution, the actions. The older methods required distinct programming layers for each of those three steps. VLA integrates them, moving the robot away from rigid, pre-programmed step-by-step logic to flexible, goal-oriented behavior that can interpret nuance. It's a quantum leap in flexible instruction.
The clearest demonstration of this new architectural thinking comes from Google DeepMind, which unveiled the Gemini robotics architecture, demonstrated prominently on Apptronic's Apollo humanoid platform. Our research highlights that they've essentially built a dual model system, which by design is incredibly analogous to how cognitive science believes the human brain works, separating high-level strategic planning from low-level muscle control.
That cognitive split is arguably the most significant architectural breakthrough this week.
Yeah.
You have two main modular components working in tandem. The first is ER 1.5, the embodied reasoning model. You can think of this as the orchestrator or the high-level brain. It receives a complex natural language goal, something like sort the recyclables on the table, and it handles the planning, the logic, and the crucial step of breaking that complex goal down into a sequence of simpler, actionable steps.
And here's where the definition of agency changes. The research team points out that this high-level brain isn't limited to its internal pre-trained memory. It can actually call external tools, much like a modern AI chatbot can access the internet.
Precisely. So if you ask it to sort recyclables according to, say, very specific local city guidelines that just changed last week, the ER 1.5 model can literally use an external information retrieval tool, in DeepMind's case, something like Google Search, to pull up the required context-specific information before it even begins to formulate its physical plan. That ability to gather external real-time context and integrate it mid-task is a monumental leap forward in real-world adaptability and independence. It's huge.
Then you have the second component, VLA 1.5, which acts as the action model or the low-level system. This is the muscle memory, basically.
Correct. The VLA 1.5 model takes the simplified, high-level, generalized steps generated by the orchestrator-like pick up the blue object and translates those into the thousands of precise milliseconds-long motor commands necessary for the physical actions. The delicate grasping, the necessary balancing adjustments of the torso, the smooth movement of the arm joints.
The most fascinating innovation here, which speaks directly to the interpretability problem in AI, is the thinking before acting paradigm. The VLA model doesn't just execute the task, it generates an internal monologue or reasoning in natural language before it begins execution.
This is the feature that excited the research team the most because of its potential for robustness and safety.
Yeah.
In a key demonstration, a robot asked to sort laundry could be observed generating the reasoning. Okay, I need to sort by color. That means putting all the whites in the white bin and everything else in the black bin. This provides immediate transparency into the robot's logic stream, which is crucial for safety, debugging, and frankly, for human trust in these machines.
But I have to challenge that point a bit. Is that internal monologue a true reflection of deep human-like reasoning? Or is it more like a generated output designed purely for human interpretability, making us feel like the robot is thinking when it's merely generating a plausible chain of logic?
That raises an important question, and the answer is likely somewhere in between. It is certainly a generated output, leveraging the underlying language model capabilities, but the key is that this generated plan is then directly fed back into the control loop. It acts as an executable plan, not just a narrative. And crucially, it enables superior adaptability. If the environment changes mid-task, for instance, if one of the laundry bins is unexpectedly moved by a passing technician, the robot can perceive the change, reevaluate its natural language reasoning, and adapt the execution seamlessly.
So it's a modular, robust, and scalable structure that fundamentally moves robotics away from opaque black box control systems and into a realm where complex behavior is governed by transparent, human-readable logic. Sounds pretty impressive.
Precisely. But a sophisticated mind is useless without massive, high-quality data to train the body. This brings us to the fundamental bottleneck. Training general-purpose humanoids requires massive, diverse data, but traditional methods of collecting it are painstakingly slow and, well, prohibitively expensive.
This is a persistent problem, right? We can build the sophisticated VLA models, but how do we quickly teach the robot the thousands of nuanced physical skills required to operate in a home or factory? That's where the Chinese research detailing the humanoid exosystem offers an incredibly elegant solution, focusing on industrializing the process of the body's education, so to speak.
This system is a novel approach to high-fidelity data acquisition. It tackles the challenge of converting complex human physical skills into machine-readable format.
Tell us about the hardware. It sounds like something directly out of a sci-fi movie, a wearable solution.
It is exactly that.
Yeah.
A lightweight, flexible, wearable exoskeleton that a human operator wears while performing a task. It captures full-body motion data, arms, torso, and legs in joint space, recording exactly how the human manipulates objects and navigates. This is supplemented by a back-mounted LiDAR sensor that tracks the operator's 6D pose in real time.
Before we move on, let's briefly unpack that term, 6D pose tracking. For a listener who's maybe not neck-deep in robotics jargon, what does the 6D represent, and why is that level of detail essential for robot learning?
That's critical context. Good point. When we talk about 3D tracking, we usually mean X, Y, and Z coordinates, position, and space. Simple enough. But 6D adds 3 dimensions of rotation: pitch, yaw, and roll the orientation. This is vital because if a robot is learning to pick up a tool, it doesn't just need to know where the human's hand was. It needs to know the exact angle and orientation of the wrist and elbow relative to the environment. Without 6D tracking, the robot might know the destination, but not the path and the exact final grip required for success. Humanoid Exo captures all 6 dimensions, effectively recording human muscle memory and translating it directly into highly accurate machine-learnable data.
So instead of painstaking teleoperation, where a person remotely pilots the robot with joysticks, a process that is inherently unnatural and slow, a human simply performs the task naturally, and the system records the essence of the movement with exceptional fidelity. What was the key breakthrough demonstrated in terms of training efficiency?
The efficiency gains are staggering. Really, they demonstrated that a robot could learn complex locomotion, like the nuanced movement required for walking while carrying a payload, solely from this high-fidelity human-captured data. The robot achieved a 100% success rate on the walking portion of a manipulation task, even if the robot had only previously learned the manipulation parts of the task through older, less efficient methods. It effectively crosses the embodiment gap between the human teacher and the machine learner.
That level of efficiency is massive, but it still relies on a human demonstrating the task. Does that humanoid exosystem, by converting human motion directly, potentially bake in human inefficiencies or even, cultural movement biases into the robot's movement? Is there a risk that these robots won't optimize for pure machine efficiency, but merely mimic suboptimal human movement?
That is the constant tension in imitation learning. You are absolutely correct. The robot is learning to imitate, not necessarily to optimize in the way a machine might traditionally do through simulation or reinforcement learning. However, the researchers argue that the benefit of rapid, generalizable skill acquisition far outweighs the small inefficiencies. Once the robot has the foundational human skill, it can then use internal reinforcement learning, or that VLA 1.5 action model we talked about, to fine-tune and optimize the speed and smoothness of that movement for its specific hardware.
So it gives the robot a first draft of a skill that is immediately usable in a human world, kind of a shortcut.
Precisely. A very effective shortcut. And the key competitive advantage comes from scale. The research showed that this humanoid exo method is so effective, it can reduce the need for expensive, real robot demonstrations by an order of magnitude. They achieved high success rates using just 5 real robot demos, supplemented by the rich exoskeleton data compared to a baseline that required 200 real robot demonstrations otherwise. This transforms robot training from a bespoke lab process into a scalable, industrial-grade data generation pipeline.
Which means data acquisition is now officially a central competitive battleground. Wow. Whoever can build the largest, highest quality proprietary dataset using highly efficient methods like humanoid exo will inherently have the biggest, fastest growing competitive advantage in general purpose robotics. These AI advancements are truly groundbreaking, but they only matter if the machine can actually survive continuous operation in the real world. As we noted, we've crossed the embodiment threshold. That means the sophisticated VLA software needs to be matched by hardware engineered for maximum durability and fine dexterity. The research team noted that in the past week, we saw a significant hardening and refinement of the humanoid form.
Absolutely. The engineering focus is definitively shifting away from showing off impressive but fragile acrobatic demos and towards proving industrial viability and minimizing maintenance costs. That's where the money is made at the end of the day. The prime example in terms of durability is Deep Robotics' DRO2 humanoid. This machine is being billed as the world's first all-weather humanoid, signaling a massive step towards deployment in unprotected environments.
All-weather sounds impressive, but when we look at the specifications, what does that mean technically for industrial buyers? Like, what's the nitty-gritty?
It means it's certified with an IP66 rating. That international certification is crucial because it ensures total protection against dust ingress. No fine particles can get into the sensitive electronics, motors, or bearings, and the second 6-min on the rating means it resists high-pressure water jets. This is a massive engineering feat for a complex bipedal machine. Seriously.
So what does IP66 open up in terms of use cases that were previously just impossible for humanoids?
Well, it immediately opens up all non-lab use cases where environmental protection is mandatory. We're talking about outdoor infrastructure inspections in rain or snow, navigating dusty construction sites, working in cold storage warehouses, or operating in high-temperature workshops where severe dust, humidity, or even accidental washdowns are common.
And the DRO2 can handle a genuinely extreme operational temperature range, from -20 degrees C to 55 degrees C. That resilience is a massive leap forward. But durability is only half the maintenance story, right? What else makes it truly ready for the factory floor?
Reliability and rapid repair are just as critical to industrial ROI.
Yeah.
The DRO2 incorporates a modular quick-detach system for major structural and functional components, such as the entire arm or leg modules.
Why is a quick-detach system a game changer? What's the big deal there?
Because in an industrial setting, time is money. Simple as that. If a robot is down for 8 hours while a technician painstakingly diagnoses and replaces internal components, that's massive lost productivity. With a modular system, the technician can swap out a faulty arm module in minutes, minimizing downtime. The faulty module is repaired offline later, drastically reducing the overall operational cost and maximizing the robot's uptime, a crucial element for scaling deployment.
Okay, so if deep robotics focused on resilience and durability, Figure AI, with its new Figure 03 model, focused intensely on refinement and dexterity, which addresses the manipulation gap between machine and human.
Indeed. The Figure 03 design overhaul included major enhancements to its sensory suites. For instance, the main vision system was significantly improved, offering a 60% wider field of view and lower latency for faster reactions. But the real breakthrough, the one that mimics human capability, is the tactile sense in the hands.
How sensitive are we talking? Can it genuinely perform tasks that require the nuance of human touch? Really?
Yes, we're talking about ultra-thin, tactile sensors embedded in the hands that can detect forces as light as 3 grams. That is literally the weight of a few paper clips or a single postage stamp. This level of sensitivity enables the robot to handle the truly delicate items. Imagine sorting fragile glass components or manipulating thin sheets of paper, or, in the viral demos, gently handling an egg without crushing them. This problem of delicate grasping has historically plagued previous generations of industrial grippers, which were often too strong or insensitive.
And the most unique feature, which speaks directly to solving real-world challenges, is the inclusion of dedicated palm-embedded cameras. That sounds interesting.
That addition solves a very common yet profound real-world issue known as visual occlusion. When a robot reaches deep into a cabinet, or its main head cameras are blocked by its own actions, say when its arms are raised high, it loses sight of the target object. The palm cameras, positioned strategically, allow the robot to maintain continuous visual awareness during complex manipulation or retrieval tasks in confined, tricky spaces. It provides an immediate feedback loop for grasping success. It's quite clever.
As compelling as these technical features are, the ultimate proof of concept isn't an impressive lab demo, it's long-term industrial endurance. And we saw a major milestone confirmed this week regarding a Figure humanoid operating continuously on BMW's X3 production line.
5 months straight. That is absolutely unprecedented. The robot has been continuously deployed, working material handling tasks for 10 hours a day.
5 months working a 10-hour shift is a serious long-duration deployment. Why is this specific time frame and environment so important for addressing industry skepticism?
Because it addresses the core question of reliability and consistency. Short demos show capability. Long deployments prove maturity. A modern manufacturing line is a high-stakes, time-sensitive environment. The fact that a general-purpose humanoid has operated continuously for months, maintaining the required precision and consistency without causing significant disruptions or requiring constant human intervention, signals that the transition from fragile experimental prototype to viable deployable technology is well underway. This is the data point industrial investors have been waiting for, really.
Speaking of compelling and highly visual demonstrations, we have to talk about the latest from Tesla's Optimus. The viral Kung Fu demonstration took the internet by storm, and it certainly set a new bar for fluid dynamic control.
The feat was undeniable. The execution of extremely fluid multi-axis movements, rapid stance changes, and, crucially, recovering dynamic balance after being pushed by a trainer. It shows a massive leap in physical control and coordination. Older robots needed slow, deliberate movements. This robot moves with, well, biological quickness.
And the claim associated with it was equally significant. Elon Musk asserted that the movements were operating entirely on onboard AI observational learning and not being teleoperated in real time. This signals a major advance in autonomous, dynamic, whole-body control.
It does, but we must exercise caution here. While the fluidity is impressive, the challenge with these highly polished demos is determining generalizability. Was this a truly spontaneous adaptive movement sequence, or was it a sequence that was learned through hundreds of thousands of hours of simulation and then reproduced flawlessly? Regardless of the answer, it established a new, significantly higher bar for demonstrating fluid dynamic movement. The visual mastery is key in this rapidly accelerating competitive landscape because it establishes a strategic narrative of technological leadership.
Seeing that dynamic control in the Optimus Kung Fu demo, or the Figure 03 handling delicate objects, is far more compelling visually than reading an IP66 specification list. These visuals are key to the competitive landscape and driving investment. If you're on YouTube right now and finding this analysis insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future.
Technical mastery and impressive demos are only one-third of the story. The other two-thirds are the massive global corporate investment and the battle for proprietary data they are now driving. Our research team noted market forecasts from institutions suggesting the humanoid market could reach a staggering $5 trillion by 2050, which provides the immense financial justification for the global corporate race we are witnessing.
That economic justification is fueling strategies focused heavily on acquiring data in the most challenging, chaotic environments and leveraging massive vertical integration. Let's start with one of the most intriguing case studies in retail.
We're talking about the partnership between 7-Eleven Japan and Telexistence for the Astra humanoid store clerk, targeting full deployment by 2029. On the surface, the driver is clearly pragmatic, addressing severe labor shortages in Japan's aging population. They want the robots to handle shelf restocking, inventory management, and potentially customer service.
But the deeper strategic objective, according to the research, is far more ambitious than just automating a few stores or solving labor issues. This is a profound data play, isn't it?
Absolutely. The hidden objective is to instrument 7-Eleven's vast network of over 20,000 stores as a chaotic, unpredictable, and therefore incredibly valuable real-world training data set for VLA models. It is an investment in data infrastructure disguised as an automation project.
Why is a chaotic retail environment superior to, say, a controlled factory floor like BMW's for this kind of AI training? What's the difference?
Factory floors are often structured and repetitive. They are predictable. Retail stores are the opposite. They feature constant, unpredictable clutter, varied, sometimes strange lighting, spontaneous customer interactions, and infinite variations of objects unboxed, crushed, misplaced, or partially hidden. Exposing a VLA model to this level of real-world disorder is the only way to rapidly teach it common sense and robust decision-making. The massive proprietary data set collected across 20,000 chaotic locations will be a core competitive asset, enabling the development of superior, general-purpose retail robotics AI that will be nearly impossible for competitors to replicate in the laboratory setting.
That makes total sense. Chaotic retail environments are the perfect testing ground for general-purpose AI. Now, on the manufacturing side, we see a focus not just on data, but on cost synergy, particularly from XPeng, the Chinese EV giant.
XPeng announced a fascinating strategy. Its fifth-generation humanoid robot will share 70% of its technology stack, including core vision systems, proprietary sensor fusion hardware, and high-performance AI chips with its electric vehicles.
70%, that's massive. What are the key implications of this deep vertical integration?
Well, it creates a self-funding, compounding competitive advantage. First, it implies massive cost savings through shared supply chains and component purchasing at scale. Second, it accelerates development by leveraging mature, automotive-grade systems that have already undergone rigorous testing for safety and durability. They don't have to reinvent the wheel, so to speak. Third, these robotics-native companies like Tesla and XPeng become their own first and best customers. They are using their factory floors as labs, continuously refining the robot technology using the very same components and processes used in their core vehicle business. This creates a loop where advances in the car benefit the robot and advances in the robot benefit automated car manufacturing. It's a powerful flywheel effect.
And finally, we saw a clear signal of corporate recognition of this physical pivot from a titan of the software world, Alibaba.
Right. Alibaba formed a dedicated robotics and embodied AI group. This is significant because it's not a small R&D project. It's a dedicated, named group signaling corporate recognition that the next critical frontier for artificial intelligence is moving it successfully from the virtual world into the physical one. This strategic move is being mirrored across nearly every global tech giant right now. It's a major trend.
When we talk to financial analysts, the ultimate question is always, does this pencil out? Can these expensive machines ever achieve an operating cost that makes them economically compelling compared to human labor?
The research team's analysis of the cost projections indicates the economic viability is rapidly approaching parity, even with current high prices. It's getting there.
Let's break down those striking numbers. The estimates suggest humanoids could operate for as low as $1.20 per hour. That's incredibly low. But that figure assumes a mass production unit price of $30,000. Is that assumption realistic? What needs to happen in component cost to hit that scale?
That $30,000 price point is the industry's target for 5 to 7 years out, achievable only with production volumes in the hundreds of thousands. Right now, estimates place unit prices closer to $100,000 to $150,000. For the price to drop to $30,000, we need two major cost reductions. Actuators, the complex motors and gears that power the joints, must become simpler and cheaper, ideally automotive grade. And sensors compute, the VLA chips and the high-resolution sensors, must benefit from the scale of the automotive and mobile phone industries. That's where the cost comes down.
But even at current estimated prices of $100,000, the operational economics are starting to make sense.
Absolutely. If we take that current $100,000 price point and assume the robot operates for 22 hours daily, allowing for 2 hours of charging maintenance, the fully loaded operational cost is estimated to be around $3.40 per hour. When you compare that number to human labor costs globally, particularly in high-wage manufacturing regions or service economies facing severe labor shortages, humanoids immediately become an economically compelling option for industrial and service tasks.
That economic efficiency, the possibility of a reliable worker costing $3.40 an hour or potentially $1.20 in the future, is the engine driving the massive corporate push from fragile prototype to mass deployment.
It fundamentally changes the calculus for any capital expenditure decision. It just makes business sense.
If you're listening on a podcast service like Apple Podcasts or Spotify, and you rely on us to synthesize these complex economic and technical shifts, we'd be incredibly grateful if you could take a moment to leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners and continue doing this deep dive analysis.
Okay, before we get completely swept away by the humanoid hype and the vision of a $5 trillion market, it's absolutely crucial to provide a context check. A reality check, maybe.
Yeah.
Humanoids, despite their versatility, are not winning everywhere, and the principle of functional specialization still dominates in specific extreme domains.
So function over form remains the rule when the environment is particularly hostile, dangerous, or just fundamentally non-human-centric.
Yes. A perfect example comes from space exploration. Quadrupedal robots, or robot dogs as people call them, are being tested by Chinese research teams for lunar exploration, specifically for mapping subterranean lava tubes. They are chosen not because they are smarter, but because they have demonstrably superior stability in rugged, unpredictable low-gravity terrain. A bipedal robot would be inherently unstable in that environment. Makes sense, right?
Yeah, definitely. And back here on Earth, we see similar specialization in industrial hazard zones where mobility needs to be prioritized over manipulation.
Right. TEPCO, the Tokyo Electric Power Company, is deploying a four-legged inspection robot in power plants. Its ability to maneuver over rubble, climb stairs, and navigate cluttered, hazardous environments like aging infrastructure or areas too dangerous for human entry is far superior to what a current bipedal machine can safely achieve. These are clear cases where a non-humanoid form factor is safer, more practical, and immediately deployable. The market is absolutely segmenting based on functional necessity, not unifying entirely under the humanoid banner. Not yet, anyway.
So while the breakthroughs in VLA and hardware are rapid, what are the primary challenges that remain? What prevents the instant mass deployment we read about in the most breathless headlines? What's holding things back?
The scale challenge is still significant, and it boils down to practical engineering constraints and physical trade-offs. First, energy. Our sources still note battery life limits as a major constraint, often reporting only 4 to 8 hours of continuous heavy-duty operation.
And that raises a crucial design question. Are engineers prioritizing power and torque, the strengths required for industrial work over battery efficiency? Is this a fundamental trade-off they haven't yet solved?
It absolutely is a trade-off. To achieve the kind of human-level manipulation and industrial strength required in a factory, you need high-power, high-torque actuators, which are inherently energy-intensive. Designers are actively balancing robot payload capacity, speed, and runtime. While wireless charging solutions like those being developed by Figure are emerging, frequent recharging or the need for tethering remains a hurdle for achieving true 247 autonomous work cycles without massive dedicated charging infrastructure.
The other major issue seems to be dexterity and precision. We can teach a robot dynamic movement, but the complexity of the human hand remains the final engineering frontier. It's just so complex.
It truly does. Reports highlight that companies like Tesla are reportedly scaling back certain Optimus production plans due to ongoing issues with the sheer complexity of the hand design. Achieving true human-level dexterity, the ability to handle an infinite variety of objects delicately, reliably, and with force feedback requires solving a deep engineering problem involving microactuators and complex materials that is still proving incredibly difficult to mass-produce cheaply and reliably. The hands are hard.
Finally, despite the impressive thinking ability and the internal monologue of the new VLA models, there are still fundamental cognition limits.
Yes, experts caution that while the VLA models and their reasoning capabilities look phenomenal, the robot is fundamentally relying on data-driven patterns and sophisticated algorithms. True common sense, the ability to handle a situation that is a complete unpredicted surprise, a truly novel anomaly, and to perform human-like abstract reasoning or deal with ambiguous social cues remains a long-term challenge for artificial general intelligence, beyond the scope of current VLA models. We are still chipping away at the problem of giving a machine the capacity for genuine, intuitive understanding. It's not quite there yet.
This has been a truly monumental week in the history of physical AI. To summarize this deep dive on Tomorrow Unveiled, we are witnessing the great convergence of three critical intersecting elements. First, the new AI brain, epitomized by Google DeepMind's VLA models, which allows for sophisticated dual-layer thinking before acting and tool use. Second, hardened hardware, like Deep Robotics IP66 rated DR02 for extreme resilience and figures sensory leap with ultra-sensitive tactile sensors and crucial palm cameras. And third, the strategic infrastructure, where global corporations like 7-Eleven and XPeng are investing heavily in acquiring massive proprietary data sets in chaotic environments to secure a compounding competitive edge. The transition from experimental prototypes to deployable viable technology is not coming, it is happening right now.
And this rapid transition brings immediate and urgent social implications. We noted the cultural difference in strategy. Japan's approach, driven by demographic necessity, views humanoids as friendly, practical helpers, emphasizing cultural nuance and politeness, as demonstrated by the 7-Eleven strategy. This necessity-driven integration contrasts sharply with the Western anxiety, which often focuses on the uncanny valley, the threat of immediate job displacement, and genuine privacy concerns associated with powerful sensing machines entering the workplace or eventually the home. Different perspectives.
So if humanoids are truly soon to be a common sight in factories, stores, and potentially even our domestic spaces, the biggest challenge isn't purely technical, it's societal.
The question shifts fundamentally from can they work to how will we work with them. Figuring out how to successfully integrate these powerful new partners into a human-built society, establishing ethical boundaries, managing labor shifts, and ensuring they understand cultural context will be the greatest endeavor of the next decade. It's a huge task ahead of us.
We love hearing your thoughts on these profound shifts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about the rise of these new machines, and if you're ready to have a humanoid robot as a colleague or a housemate. Thank you for joining us on Tomorrow Unveiled.